As we learned in the previous videos, determining the number of outcomes is an important part of determining probability. Let's look at an example. If we had the opportunity to choose 2 marbles from a large supply of red and green marbles, there would be a total of 2 possible outcomes. If we were to choose the red marble for the first choice, we would have 2 choices for the second marble, namely another red or green marble. If we had chosen the green marble, we would also have 2 choices for the second marble, either another red or a green marble. That makes a total of 4 possible outcomes. 2 red marbles for the first outcome, a red followed by a green marble for the second outcome, and a green followed by a red for the third outcome, and a green followed by green for the fourth outcome. This example introduces us to the fundamental counting principle. This principle says that if an action can be performed in n1 ways and a second action can be performed in n2 ways, the number of ways the combined actions can be performed is the product of n1 and n2. In this example, n1 is equal to 2 because we have 2 choices for the first marble. Each of the second choices also has 2 possibilities. Therefore, n2 is also equal to 2. According to the fundamental counting principle, n1 is 2, n2 is also 2. The product of n1 and n2 is 4. This is the total number of outcomes. Let's now use the fundamental counting principle again with each selection having 3 possibilities. Our first choice has 3 possibilities, a red, a green, or a blue marble. The second choice, after having chosen the red marble, also has 3 possibilities. A third choice also has 3 possibilities. This results in the first 3 possible outcomes. We have 3 possibilities for the first choice, 3 possibilities for the second choice, and 3 possibilities for the third choice. According to the fundamental counting principle, with these 3 possibilities for the first, second, and third choices, we have 3 times 3 times 3 equals 27 possible outcomes. If we determine all the possibilities for all the choices, we find that there are indeed 27 outcomes. Each of these outcomes is a permutation, which is how we will refer to them from now on. Consider the same 3 marbles, but now instead of having a large supply of each color, we have only 3 marbles, 1 red, 1 green, and 1 blue. If our first choice were the red marble, we have only 2 possibilities for the second choice, which would be either the green marble or the blue marble, since the red marble has already been chosen. If we were to choose the green marble for the second choice, then the blue marble would be the only option left for the third choice. This results in the first permutation of red, green, blue. Therefore, for the first choice we have 3 options, 2 options for the second choice, and 1 option for the third choice. Therefore, according to the fundamental counting principle, 3 times 2 times 1 equals 6. This means there will be a total of 6 permutations. And if we carry out all the possible choices, we will find that there are indeed a total of 6 permutations. This operation, to find the total number of permutations of n objects, occurs often enough to have its own name. It's called the factorial, and the operator is the exclamation mark. 3 factorial equals 3 times 2 times 1 equals 6. In general, n factorial is n times n minus 1 times n minus 2, etc. Each term is 1 less than the one before until the last term, 1, is reached. The total number of permutations of n marbles, or any n objects, is n factorial. There is one exception to this rule. 0 factorial equals 1. For the next example, we have 4 marbles. Therefore, n equals 4, and 4 factorial equals 4 times 3 times 2 times 1 equals 24. There will be 24 permutations of these 4 objects. If we were to pursue all the possible choices, we would find that there are indeed 24 permutations of 4 objects. Before we go further, we need to explore some properties of factorials. 6 factorial is, by definition, the product of 6, 5, 4, 3, 2, and 1. Similarly, 5 factorial is the product of 5, 4, 3, 2, and 1. Because these 5 items are the same as 5 factorial, we can say 6 factorial is equal to 6 times 5 factorial. Putting this in general terms, n factorial is equal to n times n minus 1 factorial for any integer n. We can apply this equation to itself and get the following result. For example, applying this to 6 factorial, we get 6 times 5 times 4 factorial. Let's observe here that 4 is 2 less than 6, and the number of terms preceding the 4 factorial is also 2, the 6 and the 5. We can then generalize this idea for any number k, where k represents the first k terms of the factorial, into this equation. Remember, the first k terms of the factorial are these, and we can solve for them by dividing both sides of this equation by n minus k factorial to get this. The first k terms of n factorial is n factorial divided by n minus k factorial. For example, let n equal 6 and k equal 2. Placing these into our expression, we get 6 factorial divided by 4 factorial, which expands to this. Notice that the 1's cancel, the 2's cancel, the 3's cancel, and the 4's cancel, leaving only the first 2 terms of 6 factorial. This expression shows up often enough to have its own notation. It is the number of permutations of n objects taken k at a time. Let's revisit our 4 objects and determine the number of permutations if taken 3 at a time. N is equal to 4 for this example, and k is equal to 3. We have 4 options for the first choice, 3 options for the second choice, and 2 options for the third choice. So the number of permutations of 4 objects taken 3 at a time is 4 factorial divided by 1 factorial, or 24. Remember that 4 is the number of objects we started with, and 3 is the number of objects in each permutation. When all the possibilities are permuted, we see that there are a total of 24 permutations, as determined from our equation. Let's try one more example where n equals 4 and k equals 2. We will determine the number of permutations of 4 objects taken 2 at a time, which is 4 factorial divided by 2 factorial, and is equal to 12. If the blue marble is chosen first, we have a red, green, and white marble for the second choice. This gives us the first 3 permutations. After completing all the permutations, we determine that there are 12, just as the equation predicted. As we've demonstrated, this equation will tell us the number of permutations of n objects taken k at a time. But some of the permutations are the same objects, arranged in a different order. These 2 permutations are the same combination, they are simply the same 2 marbles selected in a different order. The need to calculate the number of combinations is important enough for it to have its own notation, and is similar to the notation for permutations. The number of combinations for n objects taken k at a time. Now let's develop an equation for the number of combinations. Each combination in this example has 2 objects, and as determined earlier, 2 objects can be arranged in 2 factorial ways. Therefore, the number of combinations of 4 objects, marbles in our example, taken 2 at a time, multiplied by 2 factorial, will equal the number of permutations of 4 objects taken 2 at a time. This we determined earlier to be 12. When we divide both sides of this equation by 2 factorial, we get 6. If we identify all combinations graphically using different color circles, we see that there are a total of 6, just as we determined by our calculation. Let's try the same approach on 4 objects taken 3 at a time. Remember that k is the number of objects selected out of the 4. For k objects, there are k factorial permutations, and k equals 3 means that there are 3 factorial permutations of the blue, red, and green marbles. If the number of combinations is multiplied by k factorial, it will equal the number of permutations. because the number of permutations is n factorial divided by n minus k factorial, we can write this equation. If we divide both sides of this equation by k factorial, we have an equation for the number of combinations of n objects taken k at a time. The number of combinations of 4 objects taken 3 at a time is 4 factorial divided by 3 factorial times 4 minus 3 factorial, when calculated, is 4. By examining all the permutations, we find that there are 4 combinations, which is what the equation predicts.